One of the greatest scientific missions of modern times has taken a giant leap forward today with the launch at lunchtime of the James Webb Space Telescope.
What if everything we thought we knew about the universe is wrong? The James Webb Telescope just found galaxies that are too big, too old, and too evolved to exist. It's detecting signals from beyond the edge of space. A strange pulse, like a heartbeat, echoes through the cosmos. And a beam of light just bounced back from something. This isn't just science, it's a warning. Reality might be breaking, and we may not be alone. Join us. How we thought the universe worked. For over a century, we thought we had the universe more or less figured out. From the Big Bang to the birth of stars, galaxies, and planets, everything seemed to follow a sequence, a timeline rooted in logic, tested by observation, and supported by math. But what if that timeline is wrong? What if the laws of physics, the same ones we use to describe everything from falling apples to orbiting planets, have just failed us at a cosmic scale? And what if the most powerful telescope ever built has not just seen deeper into the universe, but seen something it wasn't supposed to? Something that breaks the rules. What exactly did we get wrong about the universe's past? And why are scientists suddenly rethinking everything they once believed? According to the standard model of cosmology, the universe began approximately 13.8 billion years ago in a single rapid expansion event known as the Big Bang. This wasn't an explosion in space, but rather the expansion of space itself, a point of near infinite density suddenly stretching outward. Almost immediately, the universe was filled with a hot, dense plasma of particles and radiation. As things cooled, atoms formed, and around 380,000 years after the Big Bang, light was finally able to travel freely through space. That leftover radiation is what we now detect as the cosmic microwave background, a faint glow that permeates the entire universe and acts like a baby picture of everything that exists. From this starting point, the universe expanded, cooled, and matter began clumping together under gravity. Over hundreds of millions of years, the first stars were born, and later, small protogalaxies began to form. These early structures slowly merged and grew into the vast galaxies we see today. According to this model, it would have taken hundreds of millions, even billions of years for galaxies to reach the size and complexity we observe in our local universe. That's what our models have told us for decades, that cosmic structure emerges gradually over time. The Hubble Space Telescope, launched in 1990, helped confirm much of this narrative. It showed us galaxies in various stages of development, helped us calculate the rate of the universe's expansion using something called redshift, where light from distant objects stretches as space itself stretches, and provided some of the first precise measurements of what's called the Hubble constant, the speed at which galaxies are receding from us. Redshift also allowed astronomers to determine how far away, and therefore how far back in time, a galaxy or star is. And based on this, we set limits on the observable universe, the portion of space from which light has had time to reach us since the beginning of time. To explain some lingering mysteries, like why galaxies don't fly apart or why the universe's expansion is accelerating, scientists introduced two key ideas: dark matter and dark energy. Dark matter is thought to make up most of the universe's mass, even though it doesn't emit or absorb light. It's the invisible glue holding galaxies together. Dark energy, on the other hand, is believed to be the force behind the accelerating expansion of the universe, like an invisible pressure pushing everything apart. Neither has ever been directly observed, but both fit the equations and solve the problems, for now. All of these components are part of what's called the Lambda Cold Dark Matter model, the standard framework for understanding the cosmos. It combines Einstein's general relativity, quantum field theory, and astronomical observations into one coherent picture. And until recently, this model fit almost everything we saw, from galaxy rotation curves to the distribution of matter on cosmic scales. But there's a catch. It only works if the assumptions we made about the early universe are correct. And that's where things are starting to unravel. Enter the James Webb Space Telescope, or JWST. Launched in December 2021 and fully operational by mid-2022, Webb was designed not to replace Hubble, but to look even further back in time, deeper into the cosmic past than ever before. Instead of using visible light like Hubble, Webb sees in the infrared spectrum. Why does that matter? Because light from the earliest galaxies has been so stretched out over billions of years of expansion that it's now only detectable in infrared. That means Webb can pick up the faintest, oldest signals from the most distant corners of the universe, potentially from just a few 100 million years after the Big Bang. Now, Webb found fully formed, massive galaxies where there shouldn't be any. And if they exist, then something is seriously wrong with our understanding of the universe. Impossible galaxies and the discovery that changed everything. Just months ago, scientists using the James Webb Space Telescope uncovered something so alarming that it's being described as a crisis for modern cosmology. It's not a distant theory or an abstract idea. It's actual data, fresh from the edge of space and time, showing us galaxies that simply should not exist. These galaxies are not just faint smudges or borderline detections. They are massive, bright, and fully formed, sitting where no galaxy that advanced has any right to be. The most shocking part? They existed just 280 to 300 million years after the Big Bang. Barely the blink of an eye in cosmic terms. So the question now is painfully simple. How did entire galaxies, containing hundreds of millions of stars, emerge when there was supposedly no time, no ingredients, and no physical possibility for them to exist? The James Webb Telescope, with its unmatched sensitivity to infrared light, detected several of these impossible galaxies almost immediately after it began full operations. Among them are now famous names like JADES GSZ 14-0 and MOEM Z14. These aren't just interesting finds. They are rewriting our understanding of the early universe. JADES GSZ 14-0 is currently one of the most distant galaxies ever observed, with a redshift of approximately 14.18. That places it just around 280 million years after the Big Bang. Meanwhile, MOEM Z14, at a redshift of about 14.44, holds the current record for the earliest confirmed galaxy in cosmic history. But it's not just how early they appear, it's what they are that is shaking scientists to their core. Under the standard cosmological model, galaxies form slowly. First, gas collects in halos of dark matter, cooling over time, eventually condensing into stars. Those stars form clusters, and over hundreds of millions of years, enough stars gather to form a faint, primitive galaxy. These first galaxies are expected to be small, dim, and chaotic, barely visible even to a telescope as powerful as Webb. But JADES GSZ 14-0 and MOEM Z14 are the exact opposite. They are too big, each one containing hundreds of millions of solar masses worth of stars, possibly more. They are too bright, emitting strong ultraviolet and infrared light, indicating intense star formation activity. And most disturbingly, they are too chemically evolved, meaning they already contain elements like carbon, oxygen, and nitrogen. which should only appear after multiple generations of stars have lived and died. This creates a paradox. At that point in the universe's history, there simply shouldn't have been enough time for even a single full star life cycle to complete, let alone several. The presence of these heavier elements, what astronomers call metals, suggests that stars had already been born, gone supernova, and seeded their surroundings with enriched material. That process alone should take hundreds of millions of years. And yet, here we are, observing galaxies where this has already happened, only 200 to 300 million years after the supposed beginning of time. Why is this impossible? Because based on everything we thought we knew, the early universe was still in its chaotic infancy at that time. It was hot, dense, and mostly filled with neutral hydrogen. Star formation should have been inefficient and slow, with small galaxies gradually assembling over long stretches of time. These new galaxies defy that picture entirely. They are structured, luminous, and enriched, and they exist too early, in too much abundance, to fit within any current model of how galaxies form. And they are not rare anomalies. Webb has now identified dozens of similar galaxies at similarly extreme redshifts. We're not talking about one or two flukes. We're talking about a population, a whole class of ancient, oversized galaxies that appear again and again in different fields of view. If just one of them existed, it might be explainable as a statistical outlier or a misreading of the data. But with this many, across this wide a region of space, that explanation collapses. The problem is no longer with the observations, it's with the theory. Under standard galaxy formation models, a typical galaxy converts about 10% of its gas into stars over time. This is a well-studied and relatively consistent pattern observed in thousands of nearby galaxies. But JWST has found early galaxies that seem to have converted almost 100% of their gas into stars, leaving no dust, no gas clouds, just raw starlight. That's like watching a city build itself instantly with no scaffolding, no materials left over, and no record of construction. It doesn't just raise questions, it shatters assumptions. Some scientists are now voicing a stark choice. Either we are wrong about how galaxies form, or we are wrong about when they form. One researcher put it bluntly. Either our models of early galaxy formation are catastrophically incomplete, or our understanding of the timeline of the universe is fundamentally flawed. This isn't just a debate about tweaking a few numbers in an equation. It's about whether the entire sequence of cosmic history, starting from the Big Bang and progressing through time, is based on a misunderstanding of what really happened. How could this be possible? One hypothesis is that star formation in the early universe was far more efficient than previously believed, perhaps driven by unknown physical mechanisms or environmental factors that no longer exist today. Another possibility is that these galaxies formed not from gradual processes, but from massive direct collapse events, giant clouds of gas rapidly turning into stars, without the slower fragmentation process we observe in local galaxies. But even those speculative models struggle to explain the metallicity and structure of the galaxies Webb has observed. The math still doesn't add up. There's also the idea that something about our measurement of time might be off. Maybe what we interpret as redshift, a stretching of light due to cosmic expansion, is influenced by factors we haven't accounted for. Could the early universe have expanded in a non-linear way? Could the constants we take for granted, like the speed of light or the gravitational constant, have behaved differently under extreme early conditions? These are no longer fringe questions. They're serious areas of inquiry being discussed in peer-reviewed journals and scientific conferences right now. So what is the James Webb Telescope really seeing? Are these galaxies the first real crack in the standard model of cosmology? Or are they the beginning of something even deeper, a doorway into physics that hasn't been written yet? One thing is clear: the universe is not behaving the way it's supposed to. The rules we thought were universal may have limits, and those limits may have just been reached. Or worse, maybe they've been broken completely. The Hubble sphere and cosmic boundaries. In the last century, we've operated under the assumption that the observable universe had clear boundaries, that there was a limit to how far we could see, and beyond that limit, the laws of physics made observation impossible. But what happens when a telescope like James Webb begins picking up light from regions that, according to all our models, should be beyond those limits? What if we're seeing signals from places where light shouldn't have been able to reach us at all? And what if this isn't just a fluke, but evidence that our entire understanding of space and causality is incomplete? To understand why this is so significant, we need to talk about a concept called the Hubble sphere. The Hubble sphere is the distance from Earth at which the expansion of space causes objects to move away from us faster than the speed of light. That might sound strange at first, because nothing is supposed to travel faster than light. But that rule only applies to objects moving through space. In cosmology, space itself can expand, and when it does, it carries objects along with it. So galaxies that are far enough away aren't racing through the universe on their own. They're being pushed away because the very fabric of space between us and them is stretching. Now, according to this concept, any galaxy located beyond the Hubble sphere is receding from us faster than the speed of light. The implication is simple but profound. The light from such a galaxy should never be able to reach us. It would be like trying to swim upstream in a river where the current is faster than you can paddle. No matter how hard that light tries to move toward us, the space between us is growing too fast for it to ever make progress. That's why the Hubble sphere is often described as a visibility limit, a boundary to what we can observe. But here's where things get strange. The James Webb Telescope has now detected galaxies at redshifts so high, values greater than 13 or 14, that some of them may be beyond the theoretical Hubble sphere at the time their light was emitted. These galaxies are not just pushing the edge of the observable universe. They seem to be beyond it. And yet, somehow, we're still seeing their light. That should not be possible under current models. It raises a critical and deeply unsettling question. Are we witnessing light that has traveled from outside our own cosmic horizon? To complicate things further, it's important to remember that the Hubble sphere isn't a fixed distance. It changes over time because the universe's expansion rate changes. In fact, during earlier cosmic epochs, the rate of expansion was different than it is now. That means the current boundary of what we can see, often referred to as the observable universe, is shaped by the interplay between light travel time and how quickly the universe was expanding when that light was emitted. What this boils down to is that the universe's visibility limit is dynamic, not static. Still, even taking that into account, there are emerging cases where the data seems to violate our expectations. In particular, the light from certain galaxies appears to have traveled farther than it should have been able to, based on their age and redshift. Some scientists have proposed that we might be seeing light echoes, photons that didn't take a direct path to us, but instead bounced or curved through warped regions of space, possibly due to extreme gravitational lensing, cosmic curvature, or even some unknown boundary. This leads to a more radical but increasingly discussed possibility. We might be witnessing non-causal light, signals that don't obey the standard rules of cause and effect as we understand them. In physics, Causality means that an effect cannot occur before its cause. But if light is arriving from beyond the Hubble sphere, and doing so in a way that can't be explained by simple expansion models, then we may be dealing with phenomena that sit outside the normal framework of space-time. Could it be that the James Webb Telescope has glimpsed structures that aren't just distant in space, but fundamentally outside of our causal universe? One explanation gaining traction among cosmologists is that the universe might have a looped or closed geometry. In a closed universe, space curves back on itself, like the surface of a sphere. That would mean light could eventually circle around and reach us from the opposite direction. Not because it crossed through infinite space, but because it followed the curvature of the cosmos itself. This would explain how light from apparently unreachable regions could still arrive. Not in violation of the laws of physics, but by following a path we didn't previously consider. Another possibility involves non-linear time. The idea that time, like space, might not be a straight line. While still speculative, some theoretical frameworks suggest that time could bend or fold under certain extreme conditions, much like space does around massive objects. If time itself warped in the early universe, light could have followed unusual paths that make it seem like it originated farther away or earlier than it actually did. This could also help explain the strange age and development level of some of the galaxies James Webb has detected. There are also discussions about multi-connected universes, models in which space isn't infinite, but instead connects back on itself through higher dimensions. In such a model, light could move from one point in space to another through a shortcut, or wormhole-like fold in space. This would blur the line between what we consider near and far, or even between past and present. If these theories hold any truth, then some of the light we're seeing may not have taken the journey we think it did. It could be arriving from elsewhere, not just from another location in our universe, but from another region of a larger structure we don't yet understand. All of this remains deeply controversial, and scientists are being careful with their claims. No one is saying definitively that we've seen past the edge of the universe. But what's becoming increasingly clear is that James Webb's observations are straining the limits of what our current models can explain. The idea that the observable universe is a hard boundary, that beyond a certain point nothing can reach us, may no longer hold up. And if that boundary is more flexible, curved, or fragmented than we believed, then everything we thought we knew about the shape and size of reality is suddenly back on the table. The universe might be larger, older, and more deeply connected than we ever imagined. Or it might be far stranger than that. What if the universe never had a beginning? If galaxies like JADES GSZ 14-0 and MOM Z14 existed only a few 100 million years after the so-called beginning of the universe, and if they already contained complex chemical elements and fully developed structures, then it forces us to confront a radical possibility. What if the universe never truly began? What if the Big Bang, long thought to be the origin point of space and time, was not a beginning at all, but simply a dramatic transition from something that came before? And if that's true, what exactly came before everything we know? More and more physicists are beginning to question the idea of a singular beginning. The classic Big Bang theory suggests that all of space, time, and matter emerged from a singularity, an infinitely dense point, around 13.8 billion years ago. But singularities, as they exist in mathematics and physics, are places where our equations break down, and the laws of nature cease to function in any understandable way. In other words, the Big Bang singularity might not be a real event, but rather the limit of our current models, a gap in our understanding, not the absolute origin of everything. Some theorists now argue that what we call the Big Bang was actually a bounce, a violent phase transition in a much older and possibly eternal cosmic cycle. What if the timeline we've constructed, starting from zero and moving forward through expanding space, is only part of a larger structure that extends in both directions? In this view, our universe may be one era in a sequence, preceded by a contracting universe that collapsed before bouncing into this one. These so-called cyclical models of cosmology propose that universes are born, expand, cool, and collapse again in an infinite rhythm. In that case, the James Webb Telescope might not be looking back at a beginning, but at the debris of a universe that came before ours. That would mean our earliest galaxies aren't early at all. They are leftovers, fossil structures that survived or re-emerged after a cosmic reset. One implication of this is that time may not be linear in the way we experience it. While we think of time as a straight line from past to future, models that incorporate quantum gravity or string theory often describe time as dynamic, capable of bending, looping, or even reversing under certain conditions. In string theory, for example, space and time may exist as part of higher dimensional branes, where multiple versions of reality can coexist, intersect, or collide. This introduces the possibility that JWST is not simply observing our own timeline, but is capturing light and matter from an overlapping timeline, an alternate region of the multiverse that is bleeding into our own. Some physicists have gone further, introducing the idea of a fractal universe, where the structure of space-time is self-similar at different scales and may contain repeating patterns across different epochs. In a fractal cosmos, what appears to be a beginning may simply be a small-scale echo of a larger system. That means the conditions that created galaxies hundreds of millions of years after the Big Bang might be repeating echoes of cosmic events that have happened before, possibly many times. In this scenario, JWST could be observing light not from one universe's infancy, but from a pattern that plays out across multiple cycles, where galaxies evolve, dissolve, and reform in similar configurations. So, what exactly is JWST picking up? Could it be that the strange galaxies it has observed, those that are too evolved, too bright, and too large for their age, are not anomalies at all, but evidence of pre-existing cosmic memory? Some scientists speculate that JWST might be capturing reflections or echoes from earlier cycles of the universe. These echoes wouldn't be like sound waves bouncing off a wall, but distortions in space-time caused by repeated structure, like gravitational fingerprints left behind by previous universes. These patterns could be encoded in the cosmic microwave background or in the distribution of galaxies across space. And if they are real, they may hint at a universe with no true beginning and no ultimate end. It's even possible that what we are seeing are resonances across dimensions, patterns that appear in our universe as a result of deeper geometries in a higher dimensional space. In string theory and M theory, these dimensions are not metaphorical. They are mathematical necessities, invisible only because they are compactified or hidden at scales we can't yet probe. If these extra dimensions allow for timelines to intersect, then Webb may be detecting light that originated in a nearby but fundamentally separate reality. This raises another disturbing possibility. If our universe is part of a larger cycle or structure, then what we call natural laws may not be constant. Physical constants like the speed of light, gravitational strength, or the fine structure constant might change from one cycle to the next, or from one region to another. That means the physics we rely on to explain galaxies, stars, and atoms might only be local rules, not universal truths. And if those rules can change, then the entire scientific framework we've built, from quantum mechanics to general relativity, might only apply to a small patch of a much larger, more chaotic structure, the cosmic pulse and the chilling echo. Among the strangest and most unsettling signals detected by the James Webb Space Telescope is what some researchers are now calling a cosmic pulse, a faint, rhythmic frequency picked up during background noise analysis. It is not random, it is not chaotic, and it does not resemble anything we've catalogued before. It's not a pulsar, not gravitational waves, and not cosmic microwave background interference. This frequency repeats at precise intervals, with a mathematical consistency that has left scientists puzzled. In simple terms, it's as if something out there is beating, like a heart, slow, subtle and steady, embedded in the structure of the universe itself. What could generate such a signal? One line of speculation points to exotic physics, phenomena predicted by advanced theories like string theory or loop quantum gravity. In this view, the signal could be the result of vibrations in higher dimensional space, rippling into our own reality like echoes from a deeper layer of existence. Another, more provocative theory suggests the frequency may be encoded, not just a product of physics, but a form of communication, intentionally or unintentionally broadcast across the cosmos. Though there is no direct evidence of intelligence, the precision and regularity of the signal have led some theorists to consider whether we are detecting a signature of design, something akin to a cosmic metronome, left behind by a civilization or by the universe's underlying architecture. Adding to the mystery is a second, entirely unrelated anomaly: a cosmic light echo. Astronomers had been tracking a distant signal, a fading light source from near the edge of the observable universe, when something unexpected occurred. The signal reappeared, not in the same location, not from the same time, but with the exact same spectral fingerprint, as if the light had bounced off something and come back. This should be impossible. Light traveling through open space continues in a straight path, growing fainter as it spreads. It does not bounce back, unless it hits something. There are only two serious explanations on the table. One possibility is that the light looped around a closed, curved universe, bending through cosmic geometry and returning from another direction. A bit like circumnavigating a planet and ending up back where you started. The second, far more bizarre possibility is that the light reflected off something. A boundary, a surface, a structure at the edge of the universe. If true, that would suggest our universe may not be infinite, but contained, possibly even engineered. This has reignited interest in simulation theory, the idea that the universe may be a construct, governed by code, limits, and artificial boundaries. While no one is claiming definitive proof, the combination of a rhythmic cosmic pulse and a reflected light echo is deeply troubling. It raises the unspoken question: if the universe has a heartbeat, who or what is listening to it? Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.